Harnick, and this is my presentation on iterative methods on solving linear systems, the Gauss-Sidel method and the Jacobi method. So first, I'm going to start off with just a brief overview of my presentation. I'm going to go into the Gauss-Sidel method, examples of it converging and diverging, then the Jacobi method, examples of that converging and diverging. Then I'm going to go into a code and model for both methods, why it works. I'm going to explain my code and give further examples for both methods. And then I'll talk about applications for more specifically the Gauss-Sidel method. And finally, I will go into a convergence analysis of why and under what conditions the Gauss-Sidel, the Jacobi method, and iterative methods in general converge. Okay, so first we have the Gauss-Sidel method. The Gauss-Sidel method is based upon a square system of n linear equations represented by ax equals b, where a times x is equal to b. A and b are given. This would be how a and x multiply out to get b1, and this will just go down for the entire system of equations. And x naught gives the initial guess for x, and it's often just set to the zero vector, and it will be in the majority of my examples. And x to the k is just given as the kth approximation for x, because these are iterative methods, and we are just iterating towards x when we converge. And so for the Gauss-Sidel method, we use the matrix-based formula. X of the next approximation is equal to L inverse times b minus u times x to the previous approximation. And this is one step of us iterating towards the next solution. And in this, I did not define L or U. So L is a lower triangular matrix, including the diagonal, and U is an upper triangular matrix without the diagonal, where L plus U are simply equal to A, or our initial matrix representing the system of equations. And the way we derive this and why it works is because we start with ax equals b, as we had, and we can split A into L plus U as seen above. And after that, we distribute x onto L and onto U. And then we subtract ux from one side. And then we just multiply both sides by L inverse, and we're left with this equation where we're acting all of these things on x to get the next iteration of x as we're approaching what actually solves the system of equations. Again, this is given that the system converges. And so going into our first example, where the Gauss-Sidel method leads to convergence, we can see that right here, our first equation, 2x1 plus x2 is equal to 1. And our second equation, x1 plus 2x2 is equal to 2. And given this system of equations, we get a equals 2, 1, 1, 2. X is x1, x2, and b is 1, 2. And so we're going to start with the initial guess of x naught is equal to 0, 0. And first, we're going to find L inverse and U. And so first we have to find L, which would be 2, 0, 1, 2 in this case. And U would just simply be that other value. So 0, 1, 0, 0. And going through finding the inverse of L, I've already calculated it. We get 1/2, 0, negative 1/4, and 1/2. And we simply go and we iterate until the residual is small enough. In this case, we're going to go until we can see a clear pattern that it does converge. And we're not going to set a residual, but that is something we'll do in the code, where a residual is just the difference between one iteration and the iteration after it. And once that reaches a certain value that's small enough, we'll stop iterating. And so we simply start mathing it out, where we get L inverse, as we can see right here, and we place it at the front, and we get B, which is 1, 2 in this case. We get our upper triangular matrix, 0, 1, 0, 0, and we get our initial guess for x. We place it right here, and we do the math, and we are left with 1/2 and 3/4. And then we plug that into the next spot, leaving everything else the same, and we iterate forwards again, being left with 1/8 and 15/16. We plug this in, we do it again, and we do that one more time. And then after this, I wrote, we can see this will converge to 0, 1. And this is because of the pattern that we can see in this equation, that I'm going to illustrate right now. So we start, our first iteration gets us to 1/2 and 3/4. And our next iteration gets us to 1/8 and 15/16. And then we go to 1/32 and 63/64 before finally going to 1/128 and 255/256. And what we can see throughout these 4 iterations is each time these values are growing by a factor of 4 closer to their respective results. So 1/2 gets divided by 4 as it approaches 1/8, and then gets divided by 4 as it goes to 1/32, and then gets divided by 4 as it goes to 1/128. And this, if you were to keep iterating, we would just see 1/128 will just get divided by 4, and that would keep happening until it approaches 0. And for the value of x2, we can see we go from 3/4 to 15/16 to 63/64 to 255/256, where again we're getting closer and closer to 1 by a factor of 4. We're multiplying the denominator by 4, and the numerator is staying 1 away from the value of that denominator. So it's getting closer and closer to 1. And again, if you were to keep iterating the function, you would see that this approaches 0, 1. And above, I had it written out, whereas if x1 is 0, we get 0 plus, switch the laser pointer, we get 0 plus 1 is equal to 1, which satisfies the first equation, and then we'd get 0 plus 2 is equal to 2, which would satisfy both equations, and we can see that this convergence would yield us the correct answer. And so now going to the example for divergence of the Gauss-Sidel method, we can see off the bat that it's not going to work. Our equations are x1 plus x2 are equal to 1, and x1 plus x2 are equal to 2, which you see this is never going to work, as the same equation cannot equal 2 different values. And so this would yield us a matrix A is equal to 1, 1, 1, 1, X is equal to x1, x2, and B is equal to 1, 2. And we're going to let our guess stay the same. X0 is equal to 0, 0. And we're going to find our lower triangular, our upper triangular, and again, the inverse of our lower triangular, which would be 1, 0, negative 1, 1. And we're going to plug it into the equation. We start 0, 0. We iterate, we get 1, 1. We put 1, 1 in. We iterate, we get 0, 2. And we keep doing this. We get negative 1, 3, negative 2, 4. We get negative 3, 5. And we can see this diverges because every time we put it in, we start with 1. Write this out as well. We start with 1, 1. Then we go to 0, 2. Then we go to negative 1, 3. And then we go to negative 2, 4. And finally, we go to negative 3, 5. And we can see for all these, the value of x1 is decreasing by 1, whereas the value of x2 is increasing by 1 every time. And again, this is just going to keep going on off into infinity, where eventually it's going to be negative infinity, positive infinity, and clearly that diverges. Okay, that sums up the Gauss-Sidel method. Now we're going to go into the Jacobi method, which is very similar. So again, we're representing a square system of linear equations. Again, they're represented by ax equals b. And again, we're using a similar formula, but it is slightly different. Whereas this time, A is split into a strictly lower and a strictly upper triangular matrix where the diagonal is omitted from both, and we're left with D, which is just our diagonal matrix. And the formula for this is derived very similarly to the Gauss-Sidel method, because we split up A into 3 parts, we distribute X again, and we just subtract L and U together right here, and then we multiply by the inverse of D this time. So we're doing the same thing, just in a slightly different way. However, the way the results differ are super, super interesting, and we'll see that in the convergence and divergence examples for the Jacobi method. So first, going to convergence, we have the same equation as above. We have 2x1 plus x2 equals 1, and we have x1 plus 2x2 is equal to 2. And I took the liberty of combining the L and U matrices here that we came up with from our equation into one matrix that I called R. But to get those L and U matrices to begin with, we have AX equals B from this linear equation system, and we can see the lower triangular is just the 1 in this value, the upper triangular is just the 1 in this value, and our diagonal matrix is just the diagonals, so 2, 2, whereas the inverse of that is 1/2 and 1/2, where the rest of the values are zeros. And then again, we combine the L and the U to get this R. We just plug that in right here. So the arithmetic is going to look very, very similar here. We just plug in our initial guess, we do the math, and we get our answer for the next iteration. And then plug this in here, and then we get our answer. And we just continue on. We do the same thing. We plug it in, and we get our answer. And we plug it in, and we get our answer. And one last time, we plug it in, and we get our answer. And so here, again, got the same solution that is converging towards 0, 1. But I want to really explain the pattern here and show how it's different. So our first iteration leaves us with 1/2, 1. And then we're left with 0 and 3/8. And then we're left with 1/8 and 1. And 0 and 15/16. And finally, we're left with 1/32 and 1. And I'm arguing again that this converges towards 0, 1. We already know that this equation does result in this answer, but the pattern here represents differently because instead of both x1 and x2 growing closer at the same time, we can see that in half of them and every other equation, that x2 is actually equal to the value that it will be, and in the other half, x1 is equal to the value that it will be, where the values are just growing closer that aren't equal to the value that they should be. They're growing closer to that value every time it iterates on that half of the pattern. So we can see here for the first one, we have x1 is equal to 1/2. And then the next time we get to that where x2 is correct, x1 is equal to 1/8. So it decreases, it gets closer by a factor of 4. And then it's equal to 1/32. And if we were to keep going, this pattern would continue. And for the other half, so for our second and fourth iterations right here, we can see that x1 is correctly at 0, but x2 is 3/8 the first time, then it grows closer to 1, going to 15/16. And again, if we were to continue to iterate, it would only get closer and closer to 1. I just thought that was super interesting how that works and how it is kind of shows a biphasic pattern as opposed to the more consistent linear pattern of the Gauss-Sidel method. And so going to the divergence for the Jacobi method, we see the same thing. So we have the equation that we use for divergence of the Gauss-Sidel method. X1 plus x2 is equal to 1, and x1 plus x2 is equal to 2. Obviously, this isn't going to work. And so setting up our A, 2 by 2 matrix of 1s, and then x, x1, x2, and b, 1, 2. We find our diagonal, which is just the identity matrix. So the inverse of that is also the identity matrix. Our lower and upper triangulars are this. So our combined R would just be 0, 1, 1, 0. And our initial guess is again 0, 0. So here, our first iteration leaves us with 1, 2. And then we get negative 1, 1, 0, 3, negative 2, 2, negative 1, 4, and negative 3, 3. And here I wrote, we can see this diverges. And again, it's because both values are moving away from each other, just like what was happening in the Gauss-Sidel method. But again, I want to highlight this pattern where it's almost two patterns in one. We have 1, 2, and then we have negative 1, 1, and we have 0, 3, and we have negative 2, 2, and then we have negative 1, 4, and then we have negative 3, 3. And so we're going to just put the brackets around all of these. And so we can see on both halves, x1 is decreasing by 1 every time. And x2 is equal to x2 plus 1 every time. But they're just starting from different points. And again, I thought this was just really cool how it presents differently, but we can see it diverges. And interestingly enough, this is the same pattern that is happening with x1 and x2 if you go back up to the example of divergence in the Gauss-Sidel method. X1 is decreasing by 1 and x2 is increasing by 1 every time. And so they're both diverging. The same pattern is happening, but the Jacobi method has that um, biphasic pattern where it's split into two parts for both convergence and divergence, which I thought was really interesting given the same solutions and the same system of equations. And now I'm going to get into the code, but before I do that, I'm going to explain the element-based formulas for the Gauss-Sidel and the Jacobi method. I think this is helpful because it helps better explain the code and makes more sense of what is going on mathematically behind it. So this is just the formula, like using summations that results in the Gauss-Sidel and the Jacobi method. And so you can kind of see the Gauss-Sidel reflects the matrix method as I explained. So we have L inverse, which has a similar scaling effect to 1 over the diagonal of the x value. And so this just is reducing the value of this to get the correct term that we should have. And so where here the inverse scales it down, here it's 1 over the diagonal. And here we have the value of the b vector, and here we have the b at that instance for x. So if it's x1, then it's b1. And then we're subtracting the summation from j equals 1 to I minus 1 of aij times x to the new term, where x to the new term is like the newest x value. So that would be x to the k plus 1. And then we subtract j equals I plus 1 to n of aij to x to the old term. And what this is doing, having these two summations, is if we have x1, x2, x3, xn, and we're solving for x3 here, what's happening is that for x1 and 2, we're using the new term, we're skipping over x3, and then for the rest, we're using the old term. And this allows us to more quickly go through and accurately find iterations faster. It also allows us to store less because we're storing this concatenated matrix, concatenated vector of the new x's and the old x's instead of needing both at the same time. Whereas, as we can see in the Jacobi method, we're just combining these two summations into one, where we're just using the old term. So we're storing the new one and the old one until we completely fill out the new one. So it's taking more storage space, the computation is slower, and it's a little bit less precise immediately because we're waiting to use our new values of x. And this will reflect in the code, and these summations and formulas will be shown in the code. And I just wanted to highlight that before I go to the code. So now I'm going to switch over to the code for the Gauss-Sidel method. So we define a function, and the parameters are the coefficient matrix A, the right-hand side vector B, the tolerance for convergence, and the maximum number of iterations before it's saying that it diverges. It's going to return the solution vector x. And so first, this line of code just sets a number or variable equal to the length of B, and we set x equal to a 0 vector of that length, just so everything matches up. And then we do for k in range of max iterations, so we do 100 iterations, we make x old a copy of x. So we store the old value for the convergence check. And then for I in range n, so this is the actual equation we had. We get the first summation, which is the sum of aij times x to the j for j is less than I. And then we get the second summation using the old value, as you can see right here. It's the sum of aij times the old j for j is greater than I. And then we do the calculation right here. We have that division value that was on the front before. We just moved it to the back. And then we have b minus the first summation and then the minus the next summation. And that's equal to xi for length of n. So we do this for every x in the vector, and then we check for convergence. So if x minus x old is less than the tolerance, we say it converged in that many iterations, and then we return x. And then if that never happens, so after 100 times, we print that there wasn't convergence and we return x. And here's an example of it converging. If I run the code, it converges in 20 iterations with the solution right here. And then here's an example of it not work of here's another example of it working. We're actually just going to ignore that first example. I'm very sorry about that. Here's an example of it working. Converges in 25 iterations, and it returns 1.8 and negative 2.2. An example of it not working is this, where it just diverges and that we don't reach a convergence value. And you can see these values are getting very big, or yeah, they're just getting very big. And then here's my definition for the Jacobian, which is the same parameters, same function. The only different thing in this code here is that there's that one summation instead of the double summation. And if we make sure we run this, make sure it works, we can see this converges right here to this value. And a divergent example, we can see it diverges to this value. And we can see again, these values are getting very, very large. And that's my code. Thank you. Okay, now that we've went over the code for the Gauss-Sidel and the Jacobi method, I'm going to go into applications, more specifically of the Gauss-Sidel method. This is because, as we saw above with the code of implementation and the element-based formulas, the Gauss-Sidel method can iterate a little bit faster, and it takes up a little bit less storage space, as we demonstrated showing this with the faster iterations, and as I explained with the storage space. And we're going to go into some general benefits of the Gauss-Sidel. One, it's efficient with sparse matrices where there's a lot of zero values, as to compute less. And it's a pretty simple algorithm. We don't need any advanced data structures. And finally, as I just stated, it converges faster than the Jacobi method in many situations. And a little bit of general cons. One, obviously, it doesn't always converge. And two, the initial guess can be very important. I think I failed to point out an example, but even though they were simple 2x2 matrices in the systems, they took 25 iterations to go through. And that was just with a 0-0 initial guess. And so the initial guess can be very important for how much computing power it takes the Gauss-Sidel method. And I just want to go over 3 uses that I thought were particularly interesting to me. The first being numerical solutions of PDEs, which when people go through and they solve a PDE, it can result in a system of linear equations. And this is especially useful in fluid dynamics, as their PDEs often result in something like this. And we can use the Gauss-Sidel method to solve these linear equations. Secondarily, in circuit analysis, using Kirchhoff's equations for circuits, we can get, again, a system of linear equations. I think we're seeing a theme here. And then plugging that in to the Gauss-Sidel method, we can get node voltages for those circuits, which are useful for numerous things in electrical engineering. And finally, in economics, this is the one I found the most interesting because I'm also taking some classes working in game theory and economic models, and those give us systems of linear equations, again, very often. For example, a game box normally looks something like this. We have a 2x2 with company A here and company B here, and these are the actions they can take. And this gives us a system of linear equations, and sometimes if there's another action, game box will look like this, giving 3 actions each. And as you can see, this looks similar to a square matrix, which I thought was just a cool visualization. And finally, just going into why iterative methods in general and the Gauss-Sidel and Jacobi methods converge and diverge. And so firstly, it's a blanket statement, any iterative method will converge if the spectral radius of its iteration matrix is less than 1. So first, I'm going to find an iteration matrix, and then I'm going to go into spectral radii and what they are. So first, iteration matrix. So that's just simply what is iterating the values here. And so for the Gauss-Sidel, that would just be L inverse times U, where U is this. And for the Jacobi, that would just be the diagonal inverse times L plus U, where that's this. again, just what is iterating on our function. And our second question is, what's the spectral radius? So that's the largest eigenvalue for a matrix, which again leaves us with another question: what's an eigenvalue? An eigenvalue is some value, normally denoted with this lambda, where that is some scalar where a matrix times a vector v is equal to that scalar times the vector. And so basically the matrix is acting as a scalar on the vector. And so why is this eigenvalue important? Well, if the eigenvalue is greater than 1, then it's going to expand the vector. And so this, over time, as we keep expanding the vector, is going to lead it to diverge, which obviously we don't want. Whereas if it's less than 1, it's going to contract the vector. And as we keep contracting it again and again and again, it's going to converge on some value. And then if it's equal to 1, it will just leave the same value, where obviously we don't want that, where any vector we put in is just left the same. Otherwise, we're never going to move from our initial guess. And a couple more things on the Gauss-Sidel and the Jacobi, just for other conditions for convergence that may work, is for the Gauss-Sidel, it will converge if it's symmetric, positive, definite, and if it is diagonally dominant. And the Jacobi will also converge if it is diagonally dominant, but if it's symmetric, positive, definite, that does not necessarily mean that will converge. And just to define these before we wrap up, a symmetric, positive, definite is where it's symmetric, where the A is equal to A transpose, and positive, definite means any non-zero vector in Rn, that transpose times A times that vector will be greater than 0. And this yields a quadratic form that is defined by the matrix always being positive, and this is just useful for consistency throughout calculations. And diagonally dominant just means that each diagonal is greater than the summation of the rest of the row. So just a little example on diagonal dominance would be if there's A11, A12, A13, let me have A21, A22, A23, this is 3 by 3. This would mean that A11 is greater than A12 plus A13, and A22 would be greater than A21 plus A23, and that's diagonal dominance. And I think that's all I have for you today. Thank you.